Right, in this video we're going to talk about black body radiation. We're going to talk about how a star emits black body radiation, which is all parts of the spectrum, and what we're going to notice is that certain parts of that spectrum that we observe are more intense than others. Now you could do that through, something you may have learned in AS by, using a diffraction grating to split it up into its constituent wavelengths to see all the different wavelengths, and one of those will appear more, or there'll be different ranges of intensity of those wavelengths. So we're going to observe different intensities of wavelengths. Well, what's that going to lead to? Well, what that's going to lead to is that we're going to be able to see that on a graph. Okay, so I'm going to plot a graph here of intensity against lambda. What's this showing us? This is showing us that there are lots of different intensities for different wavelengths. And right here we have a maximum intensity seen at this wavelength. And we call this lambda max. And what's useful about this is that we can use this information to work out the temperature of this star. So the temperature of the star can be found using Wien's law. Wien's law is worked out as 2.9 times 10 to the minus 3 meters Kelvin is equal to lambda max times by the temperature. Now the temperature is in Kelvin and lambda is in meters, hence meters Kelvin. So where we're going to go from here is obviously we can use that to work out what the temperature of the star is by doing 2.9 times 10 to the minus 3 divided by lambda max. Now please bear in mind that lambda max here is the value that has the maximum intensity, not the maximum lambda on the graph. That's very important that you note that, because many a student has been tricked by the fact that they're looking at the maximum value over here. It's not. This is lambda max, and this is the value we use in this equation to work out the temperature of the object that's emitting that black body radiation. So what can we do with that? Well, we can use that information. Now that we know the temperature of the star, we can use the information to work out just how big that star is. So here's our star, and obviously we now know the temperature of that star. That's good. What we want to find out is how big that star is. So we need to use a new law. We use Stefan's law. The power of the star, that's the intrinsic power, or otherwise known as the luminosity. So the luminosity in astronomy terms. So the luminosity, or the power, is equal to sigma A T to the power of 4. Sigma is Stefan's constant, so it's a constant. A is the surface area of the star, this surface area here, and T is the temperature of the star itself. So now we know the temperature of the star. If we know the luminosity, we could work out the size of it. Because remember, A is the area of this star, so it is 4 pi r squared. And that tells us the radius of the star. Well, there's one thing missing here, is how do we work out the power? Well, in a subsequent video, we're going to talk about how we get power from a Cepheid variable star. And we can obtain that power by observing the fact that a star is a Cepheid variable star. And then once we know that, we can put that into this equation to work out the size of this star, and specifically its stellar radius. So knowing the temperature from Wien's law, allows us to use Stefan's law to work out the size of this star here. And like I said in a subsequent video, my video about Cepheid variable stars, we'll have a look and see how we can obtain the power or the luminosity of stars just by looking at something very specific that they do.